Hello, everyone. Thank you for being here. So, concurrent and parallel programming is a necessity for modern applications. We have to handle a lot of users, a lot of data, and a lot of communication between our microservices. And concurrency is something that is notoriously hard to get right. So, library maintainers and language creators are always trying to make things easier for us. So today, I'd like to talk to you about Project Loom, which is an OpenJDK project aiming to bring lightweight concurrency to the Java platform. So I'm Arnaud, I come from France. I'm a software developer, and for the past 2 years, I've been involved in the development of a data-intensive application for the space industry. And we've used a lot of concurrency mechanisms, going from simple threads to reactive streams. So I'd like to invite you to the journey I went through to understand what lightweight means in lightweight concurrency. So to do that, we are going to talk about blocking and non-blocking calls. We're going to talk about synchronous and asynchronous APIs. Quickly, just a bit of reactive programming, and then Project Loom properly. So in order to experiment, I needed a use case, so I took a piece of program from work. And this is not a benchmark, so just keep this in mind, it's an experiment. So let's imagine we have a data source, and we have clients who want to download a resource from this data source. Let's say, for instance, it's a file. So because this resource is precious and we don't want to give our clients direct access to the data source, we are going to implement a service which will act as a proxy to which our clients will connect. So each time a client connects, our service will first have to talk to a coordinator in order to get an authorization to download. The coordinator manages some kind of priority queue, so this service may have to retry a couple of times on behalf of this client to get an authorization. And when finally it gets the authorization grant to start the download, it can start the request to the data source, stream the content back to the client, while at the same time sending earthbeat requests to the coordinator so it doesn't revoke our grant to download the resource. So the first implementation I have made of this service was the most straightforward one I could come up with. So I'm just showing you an example here of this getConnection method, which implements the retry loop. So first we enter an infinite loop into which we are going to try to get an authorization from the coordinator service. If it fails, we are going to update a few variables and loop to retry again. We are going to check if we haven't passed a certain deadline, in which case we will exit the method. If not, we are going to wait a couple of milliseconds, as instructed by the coordinator as a form of rate limiting, and then restart to try to get an authorization again, and hopefully get one and exit the method. So this piece of code is far from being perfect, but it has one big advantage. First, it's simple to write, as I said. Hopefully, it's easy to read, easy to understand, and therefore easy to maintain. So let's see how it performs. The CPU utilization is really low, which makes sense because in this use case, we are not computing any CPU-bound task. We are not computing any math, for instance. We are just sending a bunch of requests and waiting for the result. What's more interesting is the number of threads we are going to create. So in this simulation, I have simulated 200 clients connecting simultaneously to this proxy server. And we can see a first bunch of 200 threads created by those requests. You can then see 200 more threads which are created to handle the earthbeat requests, but this is an implementation detail at this point. And the real question is, why are we creating 200 threads? So let's see what the threads are doing. If you look at Visual VM, we will see that those threads begin with a cycle of being running, then waiting, and then running again. This is the retry loop I've shown you just before. And then when the download starts, all the threads seem to be running, which should feel weird because, as I said, they are not computing anything, so they shouldn't be running at this point. So let's see a thread dump to see what the threads are doing. The typical thread in this implementation is doing a system dispatcher that is calling a socket dispatcher, that read zero method, which actually is a system call. And they are not just running those methods, they are actually spending most of their time in it. And if we try to track the origin of this system call inside our source code, we are going to find this implementation of a basic HTTP client. In this implementation, I'm using a socket channel, which by default is opening a socket in blocking mode onto a file descriptor, and then using the input stream API to read content from the socket. So this is where the problem is, right? Because this socket channel, by opening a blocking file descriptor, will mean that each read operation made by the input stream API will issue a blocking read call. So what's a blocking call, actually? Let's assume that our CPUs run two different types of instructions, right? So the first are the user instruction, user code, and the second one are instructions from the kernel code. When we are submitting runnables to an executor service, and in this case I've used a cached thread pool executor service, which tries to match a runnable submitted in its queue with a thread, and if it doesn't find one, we create a new thread. But the threads which are created by this executor are actually not managed by the JVM itself. They are OS threads, and they are therefore managed by the kernel. And when one thread is running and encountering a blocking operation, the kernel scheduler will have to issue what's called a context switch. So most of you may probably already know what the context switch is, so I'm going to explain really quickly for the others. And to make things simpler, I'm going to assume that a context switch only consists of two steps. So the first step for the kernel scheduler will be to suspend the execution of the currently running thread. So it's going to save its call stack, it's going to save the registers it was currently accessing, it's going to save the location of its instruction pointer, it's going to put everything in a data structure and save it somewhere. It will then flag this thread as being suspended or blocked, and it will put it back into the priority queue. Next step will be to look into the priority queue which thread has the priority to run and is not blocked, so can be scheduled. And at some point later, when another blocking call or preemptive multitasking comes in, and the result of our first task is available, our kernel scheduler will finally be able to reschedule the first thread with the result of its blocking operation. And this is actually really bad, because assuming I can have thousands or even tens of thousands or hundreds of thousands of TCP connections open on a signal box, it means that each thread I'm going to, because I'm going to block each thread, the cached thread pool executor is going to try to match an incoming connection client request with a new thread, and it's going to create more and more threads because all will be blocked along the way. So all those threads that will be blocked waiting for the result of their execution to finish, they will not only consume a lot of memory, but they will also spend, they will also make you, what's the word? Waste a lot, actually a ton of CPU cycles to handle this context switch instead of running the business logic. So you may have read on the internet in blog posts that asynchronicity is a solution to this problem. So in my second implementation, I've thrown away my cached thread pool executor in favor of a scheduled thread pool executor, which by default is bound to a fixed number of threads. And basically, each of those threads in the pool will be executing an infinite loop into which it's going to grab tasks from the executor's waiting queue and execute them one after the other. So I've asynced all the things in my second implementation, and this is the result. So the connection method now takes another parameter, which is a completion handler, which is a callback. It's going to try to send an authorization request to the coordinator asynchronously from one of the threads of the scheduler. Request connection, is now also an asynchronous method, which takes a completion handler for when the result of the request is available. If the request finishes successfully, we are going to complete the callback we have been given in the getConnection method. Otherwise, we are going to reschedule another attempt to get an authorization. The big disadvantage, for this solution is that you have to manage a lot of complexity which is not inherent to the task you are trying to do. Here, I had to split my logic into several small pieces and give it 2 callbacks, where instead I should have my logic nicely bundled into a single function. But hey, if it's a price to pay to have performant and efficient services, maybe it's worth the pain. So let's see how it performs. To make things simple, I have created 3 scheduled thread pool executors to really separate who is doing what. So the first one is going to handle the connection request from the clients. The second one is going to handle the request to the coordinator service to get the authorization to download and to download the resource from the data source. And the third one is going to be used for the Earthbeat requests. Looking at what those threads are doing, we can see that the threads of the requests and Pulse executor services are spending most of their time being parked. And again, this makes sense because all the tasks we are submitting to those executor services are asynchronous tasks. So they begin to, they call, this asynchronous method, and then they return immediately. So then the threads will look into the scheduler's queue for more tasks, and because there aren't any more, because I only have 200 clients, they will just be parked, waiting for more tasks to come down the executor queue. What's more interesting are those service threads, which are handling the connections, and they too seem kind of busy, which again is weird because they're not doing anything. And if we take a look at what they're spending their time on, again we see this Tweed method. And this is on purpose in this implementation. It's because under the hood I have used the exact same function to make the HTTP request. So I am still using this SocketChannel API in blocking mode. So this was just a reminder that whatever you read on blog posts, asynchronicity is not synonym for non-thread blocking calls. All right? You can have a fully asynchronous API. If under the hood it uses a thread blocking calls, those threads will be blocked. So here you can see that the problem for efficiency is not really with synchronous versus asynchronous. It has really more to do with thread blocking versus non-thread blocking calls. But it happens that on the Java platform, if you want to do non-thread blocking calls today, you have to use an asynchronous API. So that's what I did in the third implementation of my use case. So here I'm using a java.nio API, namely the asynchronous socket channel, which by default create a socket channel bound to a file descriptor in a non-blocking mode. So I'm able to call a connect method to connect to my remote server and then write and read byte buffers when there is an action that can be done on those memory buffers. Again, it's still asynchronous, so it's really hard to read and it's indented along the way. But on the efficiency side, I'm able to handle those 200 clients with 10 threads really easily. All right, my threads, they are just, as I said, handling asynchronous calls and giving the control back to the scheduler to schedule more tasks. And because 200 clients are handled really fast, I could actually submit way more requests to this service and maybe handle them only with one thread at this point. You can see that those threads now are spending most of their time not in a blocking call, but with thread scheduling tasks or being parked. But what you can see also is this giant pile of asynchronous calls that are made, and this is because my implementation of this HTTP client asynchronous is really shitty, actually. All right, so it's not really efficient, and it could have been more efficient by using a lower level API, such as the epoll or the KQ system calls, and a pattern known as evenloop. So real quick on epoll. It's the low-level API which allows you to register monitors onto file descriptors directly in a non-blocking call, and then issue subsequent non-blocking calls to see if there is any read or write operation that can be done on those file descriptors. And this is what highly performant networking library use under the hood, such as Nettie. Nettie is a highly performant and highly efficient network library which powers a lot of microservices out there. But Nettie, although it's really awesome, it's still an asynchronous API, and you still have to split your logic and manage the callback hell. Luckily for us, a few years ago, the reactive streams specification was created, and a few libraries have been released to implement this specification. So I've used in the past 2 years one of the implementation, which is named Reactor, really heavily. And for this 4th implementation of my use case, I have used the Nettie binding for Reactor, which is named Reactor Nettie. A quick word about reactive streams. After having using them for more than 2 years heavily now, I can say I'm really dissatisfied by the way, by the reactive style of programming. Because while it's sometimes easy to map even complex problems into a simple chaining of existing reactive streams operators, sometimes it's harder to do so. In this example, which is the same retry loop I've shown you a couple of times, you can see that this retry logic, which was arguably simpler to understand in the previous versions, is now buried under a ton of reactive streams operator and in this example, 3 atomic references. And this is because I really had to scratch my head to make a stack-safe implementation which will avoid recursive calls. But on the other side, of course, it's really efficient. Right? You can see that Reactor Nettie has created 12 threads to run a KQ event loop, so just to handle events available onto the file descriptors. And the parallel executor, which is used to implement my business logic, those threads are parking, waiting for more tasks because the 200 clients are handled too fast. So the question is, can we benefit from non-blocking asynchronous calls and also of performance patterns such as the event loop, but 1, without having to manage the callback hell, and 2, without to have to do a shift of paradigm and go to reactive streams and suddenly realize that the learning curve is not is steeper than what you thought at first. So in Project Loom, they are trying to answer this question with what they call user threads. What is called user thread, right? And in Loom, user threads have been named fibers at first, and now they are starting to name them lightweight threads again. So lightweight threads, or user threads, green threads, fibers, coroutines, are actually under the hood the same concept. So the only differences I found between all those terms were in implementation details, right? Because some of them are implemented inside the compiler, some others inside runtime libraries, and some others in the form of macros. And in Project Loom, they have decided to implement lightweight threads both inside the JVM and inside the JDK. And they are basing their work on top of a concept known as continuations. So continuations are not new. They are a really famous topic in programming language literature. And they are described as, quote, the rest of the execution of a routine or a program. So imagine you have a function, and inside this function, you have the ability to insert a suspension point, a special instruction, which, when it is reached during execution, will stop the execution of the function completely. And for instance, if this task was run by a scheduler, the scheduler will be run to schedule another task. And at some later point in time, in another branch of your code, you're going to be able to grab this continuation and traverse this portal to go back to where the execution left off and start from there. This may seem a bit weird when I present continuations like that, but actually, if we think about it, when you're doing asynchronous programming, you're doing it all day long. Because when you're executing an asynchronous task and you have to split your business logic into two pieces, you're effectively passing the rest of the execution of your function as a callback to this asynchronous call. And this is known as explicit continuation passing style. So you can think of a continuation as a runnable, for instance. So it has a method run, and when a caller calls this method run on the continuation, it will execute its instructions. It will execute its instructions as long as it for as long as it reaches this special instruction, which is called yield, or if it reaches the end of the code block. But you can think about this yield statement as a return statement in a runnable. So when you evoke a return statement inside the runnable, or if you reach the end of the execution of this runnable, you are going to explicitly give back the control of the execution flow of the caller of this code. But different than a return statement, when invoking a yield, instead of discarding all the state of the runnable of the continuation and throwing away its call stack and its instruction pointer and etc., here the runtime is going to come and encapsulate the state of a continuation and save it somewhere. The caller code will be free to do anything else it wants, and if it comes back later to call the run method, then the runtime will reload the state of the continuation, and the execution will restart from where it left off after the yield instruction, and just until it reaches another yield statement or the end of the function. So it may not be obvious at this point what continuations have to do with asynchronous programming. So I'd like to give an example of implementing continuations and returning the control of asynchronous call into synchronous by giving the example of a state machine. A state machine functions more or less the same way that I've shown before. You have a caller which calls a method on the state machine. The state machine executes instructions, flips its state, and returns the control back to the caller so it can do anything it wants. If it wants, it can call the run method again. The finite state machine will execute the block of code which is related to its updated state, and then will flip its state again and return just until it reaches the final state of this finite state machine. So to be more concrete, let's see an example of implementing an iterator as the form of a state machine. So I'm going to use an integer as the state, and this iterator's hasNext method will return true just as long as we haven't reached the final state of this state machine, which here is fixed to 5. So when a caller comes and calls the next method, we are going to evaluate this switch statement and see that the original state of the state machine is 0. So we are going to flip the state of the state machine, and because it's a string iterator, we are going to return a string, for instance, A. With this return statement, as I said, we are explicitly returning the control of the execution flow back to the caller code. This caller code is free to do whatever it wants. It may or may not call the next method again, but if it does, we are going to evaluate this switch statement, and because the state of the finite state machine has been changed, we are going to go into the case 1 branch, at which point we are going to update the state of the state machine and return another string, and etc., just as long as we haven't reached the final state of the state machine, at which point the caller code is not supposed to call the next method again. This is a protocol for the implementation of an iterator. So this is a really basic example, but just imagine for a moment that in this case 0, if we were not implementing an iterator, instead of returning a string A, we will start an asynchronous call. So we will return immediately And the callback we will give to this asynchronous call will be to call the next method again. So when the result of this asynchronous operation will be available, the callback will be called, we will enter the next method of a state machine again, and we will enter another branch of the code with the result of this asynchronous operation. So what we would have done doing that would be to inverse the control from asynchronous calls with callbacks to keep our logic bundled together inside a simple function. Of course, with asynchronous call, we don't want to manage callback hell, but we don't want either to write our business logic like that as state machine, because it's not trivial for more complicated problems. And this is what continuations give us. With support from the JDK and special scheduler, a lightweight thread scheduler, the runnables we are going to submit to this scheduler will be wrapped inside continuations. And when this continuation will reach an asynchronous non-blocking call, the fibers, I will use fibers and lightweight threads in the same way in this presentation. The fibers scheduler is going to park the continuation and give as a callback to this asynchronous method an instruction to resume the continuation when the result is available. So what it gives us is the ability to write code that is synchronous yet non-blocking. This fifth implementation of my use case looks a lot like the first one I've shown you, and this is because it's a simple copy and paste. But here, because those tasks are running inside a lightweight thread scheduler, I'm not worried about the thread.sleep method and this coordinator request, because I know that inside the JDK, they have added support for continuations, so those calls won't block the thread, but will just park the continuation, which will be restarted when the result is available. As I said, all I had to do was to use a special thread scheduler, which is given by this fiberscope.background, which will probably change because the API is still a prototype, but I will talk about that later. So again, this is really efficient because we are able to handle those 200 clients with only the 12 threads created by the scheduler, which corresponds to the number of threads I have on my machine. And what the threads are doing, they are the fork join pool, one worker, n threads. Again, it's just handling events. All right, calling a synchronous method and waiting for the results. And because the waiting queue of the scheduler is quickly drained, they are parked because they don't have anything else to do. What's more interesting are the two threads at the bottom, the read poller and write poller. They are actually event loops, which are started by this scheduler, just like you saw the KQ event loop in reactive streams via Nettie. Those threads are used to detect when there is a read or a write operation which is available on the file descriptor. And the first one, the fiber unparker, is the one which is going to resume the continuations when the result of one of these asynchronous operations is available. So Project Loom at this point is still a prototype. If you want to play with it and try continuations in this fiber or lightweight thread scheduler, you can do so by retrieving or downloading one of the JDK 14 in early access on the Loom branch of the OpenJDK project. So you will be able to play with continuations. With the fiber schedulers, you will have support for continuations inside some operations of some APIs of the JDK. And if you are really interested, I encourage you to take a look at this repository, which is called Loom Fibers on GitHub by Remy Forax, where he has played a lot with continuations. He has re-implemented many lock systems or other schedulers. But if you are not really interested in the lower details and more into what Project Loom will bring as an application developer, I advise you to take a look at Quasar. So Quasar is a Java library which implements continuations and a fiber scheduler. And it has been available on the Java platform since 2013. So those lightweight concurrency mechanisms I've just talked about, they were already available on the Java platform for 6 years. Probably you just didn't know about them. And on top of Quasar, on top of the continuations and fiber scheduler of Quasar, they have also implemented a CSP model and an actor model, which really gives you a hint at where the Java platform can be going with an implementation of fibers or lightweight threads underneath its stack. You can also take a look at Kotlin's coroutines, because they are fundamentally the same concept. The differences are that Quasar implements continuations via bytecode manipulation. So it's going to take your synchronous task with suspension points and turn it into the kind of state machine I've shown you, but just you won't see it. And Kotlin coroutines implement continuations in a compiler, while in Project Loom, they are implemented inside the runtime. So of course, there are drawbacks. And here I've taken excerpts from the Quasar documentation, because Quasar and Project Loom are really similar. And the reason is because the lead developer of Quasar is now the project lead of Project Loom. So if you compare the two, you will see a lot of similarities between the two APIs. So the first limitation is that you won't be able to do thread blocking calls when running on a fiber. So they have updated a few packages, such as java.net and java.ANIO, to support the continuations. But if you have your own API which blocks threads and you want to call them inside a fiber scheduler, you are going to block the underlying thread. So all the other lightweight threads or continuations which are queued inside the executor's queue won't get a chance to run. So this is forbidden. Another limitation is with synchronized keywords, because synchronized blocks the kernel thread. They are not allowed in fibers or lightweight thread either. The solution to this, if you have access to the source code, will be to replace this synchronized keyword with an explicit lock, such as a reentrant lock, because continuation support has been added to the Java util concurrent package. So you can use a familiar try lock and finally unlock pattern with the reentrant lock. There are other limitations, but they are more advanced, and I won't have the time to talk about them. So continuations and this lightweight thread scheduler were the first step of the proposal for Project Loom. The next step was tail call optimization, implementing automatic tail call optimization in Java. But they haven't started to work on that yet, so I can't talk about it. What I can talk about is a new pattern that is being discussed currently inside the Loom working group, which is called structured concurrency. So structured concurrency is the new way to look at concurrent programming. The idea here is to give you the ability to draw a bounding context around related concurrent operations. So you will be able to cancel all child concurrent operation of a context by just canceling the scope, the context itself. Or you could decide that when one of the concurrent operation inside this context fails, you want to cancel the whole block. And you can also ensure that all the concurrent operations inside your block will return in a finished amount of time with a deadline. So if you are interested in structured concurrency, I'm going to let that as an exercise for the reader. You can go check out Kotlin's coroutines, because they have implemented structured concurrency. And you can check this blog post, Go Stateful Considered Harmful, which is really, really interesting and seems to be the seminal paper for this structured concurrency pattern. I have grouped a small number of references if you are interested to go check out what's in the literature for continuations and for lightweight threads. And I have put also a link to the Loom Fibers repository of Remiferax. And the last one is a link to my own repository, where you will be able to find all the different implementations of the use case I've talked about. And I will also put a link to the slides on Twitter after the talk, so you can find it. That's all I have. Thank you all for coming, and I'd like to address a giant thank you to the organizers. They're doing fantastic work, so please, a big round of applause for them, and I'll be around if you have questions.